life. Substitution rule. All right, so this is integration, kind of the chain rule in reverse. Okay, so we kind of saw that example I kind of messed up on earlier with the squared and stuff like that. So I was trying not to introduce that just now. But this is where you're trying to think of an antiderivative, and if you take the derivative of that, you're not looking at the function in the integral. It's close, but it's not there yet. So we got to make some adjustments to it. Let's see. Let's just dive right into it. Let's do an indefinite integral. Definite ones have limits of integration, right? So we're going to have to tackle in a plus c eventually, just because we don't know exactly what it is. So let's say if I have 2 times 2x plus 1 cubed dx. Now, we could sit here and cube the binomial and then multiply by 2, distribute it across, get a nice polynomial, do the antiderivative, and that avoids all the substitution. But you can see that this is a composite function. You have something in the parentheses, you must do that first, cube it, right, and then multiply it by 2. So there's several steps that are happening here. So you always want to identify what the inner function is. So the inner function is the very first thing that you do. Think of order of operations. Go into parentheses. That's typically the case, right? So the 2x plus 1 is going to be our inner function. So we're going to let u, substitution, you can really let any variable you want, but you can see in calculus or any kind of math, u is always the best variable for substitution for some reason. It's just going to be 2x plus 1. So if I take u as that, we need du, the derivative of u with respect to x. Okay, so u prime, that's just 2, right? If I cross multiply, so du is equal to 2 times dx, right? So now I'm going to rewrite the integral as, look right here, this 2 dx right here is du, right? This right here is u. So this becomes u cubed du. We know how to integrate that. That's pretty simple. U cubed du is nothing more than u to the 4th over 4 plus some constant c, right? Now replace what was u. U is 2x plus 1, which is to the 4th over 4 plus c. That's it. All right, so again, this is a composite function. 10 times e to the 10x. So the first thing you would have to do is figure out what that exponent would evaluate to if you were to put something in for x, right? And then it's e to that next, and then it's times 10. The 10 really, put that out in the front, it's constant, right? So see if you could do the substitution. Let u equal 10 to the x, right? 10x, sorry. Then find du over dx, and then solve it for just du. Make your substitutions. You'll have something in the form of u du. Take the antiderivative. Tack on c. All right, so du is equal to, I'm going to put du over dx, right? Let's do that first. The derivative of u with respect to x is just 10, right? So this tells me that du is 10 dx, right? Now you can kind of skip this procedure if you don't want to. Just make sure you type in what du is the derivative times dx. Remember that was, dy, that was a test question. The differential, right? Yeah. Dy over dx, and you solve for just dy. Make sure you tack on the du after you take on the dx after you take on the derivative. So now we just have this right here can be as 10 times the integral of e to the 10x, which is substitution 10 times e to the u du. And notice the 10 dx is my du right here. There's 10 dx. That's du, right? Right there. E to the u is right there. So what's the antiderivative of e to the u?
You still have a 10 on front.
The 10 still there, yeah. The 10, anything is a constant or coefficient, come right in front of the integral, or you can leave it inside it, it doesn't matter. Because it's just. Oh, wait.
Yeah.
Yes. Maybe I shouldn't have taken it out, huh? There we go. There we go. It was already there. My bad. All right, so there's my du 10 dx right there. There we go. That fixes it, right? All right. 10 dx is du. E to the u is right there. Derivative of e to the u is antiderivative, I should say, is still e to u plus c. And what is u? That's e to the 10x plus c. Right, so a little bit of a hint of what's to come. In order to do your substitutions, you always have to have the derivative of something in there as well, right? The chain rule part. Remember, you got the some function, blah, 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 and it's more than just x. You have to have the derivative of more than just that x in there, right? So look right here. We got this 10x right here. That's the chain rule part. The derivative is 10. It's there. If it wasn't there, we have to make some kind of adjustments for that. And we'll do that in a minute. But this one already had it in there. I was one step ahead of me trying to pull that 10 out. But this, let u equal, you'll see 99% of the time it's always going to be what's inside the parentheses. And that's the easiest to do. That's your inner function, right? So x to the 5th plus 6. Therefore, du is this derivative 5x to the 4th dx. Now here's where I don't see 5x to the 4th dx, right? Let's do some magic. Can you multiply a fraction by 1? Then it's always the same thing. Yeah, right. But 1 could take on many, many different forms, right? Can I do this? 5 over 5. That's 1, right? Okay. However, now I have this. It's 1/5 times 5x to the 4th. I'm just writing multiple steps here. You're going to eventually skip this. Right? This 1/5, if I pull it out, now I'm set up, right? I do have my 5x to the 4th dx in there. That's going to be my du. My x plus 6, x to the 5th plus 6 is my u. So this is now as the substitution of 1/5 times the integral of u to the 9th du. Antiderivative u to the 9th, u to the 10th over 10, plus some constant c, right? If I distribute the 1/5 across, this is u to the 10th over 50. And 1/5 plus some constant c is still some constant c. You don't have to say 1/5 of c. It's just a constant. And then replace what u was. U was x to the 5th plus 6, all to the 10th now, over 50 plus c. So if you're calculate your du, you don't have the full expression. in terms of x dx in there. You can make an adjustment by adding in a fraction that's equivalent to 1. And again, like you're going to eventually skip this step right here. You're going to say, I needed a 5, so I need to take out 1/5. Right? So if I multiply by 5 in there, I divide out by 5. If I needed to have 5 in the denominator, I'll throw in division by 5 in the integral, and then I'll throw out multiplication outside the interval. Right? So that still is totaling to 1. Put some trade, the crap, huh? Now, a lot of times with the trig functions, it's not so easy, and especially with this one, the argument for both trig functions is still x, right? It's not more than just x, but there is no antiderivative to where I could say I could take the derivative of that and get cosine cubed x times sine x. And there's nothing that strikes anything, right? It's just, so what you can do is make a substitution. So we'll let u equal, okay, for these, you might say, okay, which one I choose? It's kind of a little bit of a trial and error sometimes, but I'll tell you, for the most part, you're going to probably pick the more complicated one that has the power on it, because the same thing like we just had, you take the cosine of x and then it gets cubed. So you think about it that way, and that is your inner function, right? Just looking at it as cosine cubed x, maybe even rewriting it this way makes more sense to people to see how to get the substitution. Because cosine x times cosine x times cosine x is cosine cubed x. So that's going to involve a little bit of chain rule you can see in there, because all that was involved with the parentheses, right? So our substitution is going to be cosine x. So du is going to be, what's the derivative of cosine? Negative sine x, and the du would be negative sine x dx. Okay, it's almost there, right? We're just missing a negative. So think about, this is nice when you have different colors. I can throw in a negative 1 right here, but to keep it equivalent, I need another negative 1, right, on the outside. You can put it on the inside too, but it's a constant, so it's coming out. Negative 1 times negative 1 is positive 1. That's the same equivalent integral, no problem. Now I have everything that I need. Here's my u, and there is my du. So this is negative 1 of the integral of u cubed du, which is negative 1 of the antiderivative is u to the 4th over 4 plus some constant c. And you rewrite what is u? Cosine x. All to the 4th, let's just put the 4 right there. And there's your antiderivative. All right, let's look at the definite integrals. This is the same exact way. That's all we're doing, is now we're going to put some upper limits and a lower limit to evaluate in. All right, this is definite integral from a to b, which is 0 to 2, of dx over x plus 3l cubed. I never was a fan of writing this like this. I always like my dx to be on the back end. You can rewrite it that way if you want, because this is the same thing as 0 to 2 of 1 over x plus 3 cubed times dx, right? So if you want it like that, that's fine. Either way is still equivalent. Just my personal opinion, I just liked it that way. I think maybe that's how I learned it. Who knows how long ago now? But I will make a substitution, right? Because there's no way I can find the antiderivative of that. I don't know what it is. All right, so u is equal to parentheses x plus 3. Du is equal to, okay, derivative of x is 1 times the dx, right? We do have 1 dx in there. So it's an easy substitution. So this goes from 0 to 2. All right, this is representing 0 to 2 is x, right? So is it 2 and 0 as my upper limits? 0 as my limits of integration. This is for x, this is for x. I'm making the substitution, this is for u. So I don't put 0 to 2 anymore, because u is equal to x plus 3. So my lower limit is 0 for x, gives 3, and u is equal to the upper 2 plus 3, which is 5. So this is going to go from 3 to 5 now. So if I'm going to change using a substitution, my limits of integration have to change as well. And now I say, okay, it was 1 over u cubed du, right? 1 dx. Which that's u to the negative 3, right? So from 3 to 5, u to the negative 3 du. And now I could take the antiderivative of that. Add 1, divide by the new exponent, right? So this is going to give me u to the negative 2 divided by negative 2, evaluated at 5 minus the evaluation at 3. And I'll rewrite that so we don't have negative exponents. This is negative 2u squared in the bottom, 1 on the top. Which this is 1 over negative 2 to the times 5 squared minus 1 over negative 2 times 3 squared. That makes negative, that's 25 times 2 is 50. That's 9 times 2 is 18, minus the negative is plus 1/18. Common denominator, all that stuff gives you 8 over 225 is your final answer. Plug it in calculator, I guess, and evaluate it and change it back to fraction if you want, or do it by hand. All right, your turn. So u would be
X squared plus one.
x squared plus 1. So therefore du is 2x dx, right? Right. So I don't have a 2x dx, I have x dx in there. So we can make a substitution in there, right? So let's do something like this. Let's put it back red. I'll put my substitution in green. If I throw in a 2 on the top, that's multiplying it. I'm going to divide by the 2 on the outside. Yeah.
So like, could you rewrite like our dx? What I did du over 2x. Like it's like I think I substituted the dx for du over 2x, and then could you like move over?
So you substituted the du.
So like you can like put like divide the 2x out, so like du over 2x is equal to dx. So like you substitute that.
Yeah.
And then
Yeah.
and then because of the x and the x on top, you can like take it off and then move that 2 out as a coefficient.
Yeah. It's doing the same thing.
Okay, well, I
Yeah.
just wanted that because like
Yeah.
that's how I was.
Just how you see it.
Yeah.
When I was taught it, it was just like, I remember my teacher would just throw in these numbers and like, well, where are you coming from? You just giving it like, they didn't have an explanation about the substitution. It was just, didn't even do a substitution. It just went in straight, threw in this and threw in that and antiderivative. Oh. And now, I don't know, it's just different ways it's taught and whatever you see fits. I'm gonna say this method I see. But like you're saying, you saw for dx equals du over 2x,
Right.
right? And put that right there, du over 2x, and then you have it. You take this 2, take it out. Yeah.
Yeah.
All right, so just keeping in mind that you always want it to be always equivalent. So whatever you're taking out and putting in, always should multiply out to be 1, right? And so whatever you got to leave in, that's going to be substituted for the du right there. So we got 1/2 of the integral of du over u, right? Which is 1 over u du. If you like it like that.
Yeah.
And now what's the antiderivative of 1 over u? Natural log. And we got to go ahead and put my limits of integration. I kind of forgot to put them in there, but we went through the antiderivative. So this is natural log of u. All right, let's go back and get the limits. This is x equals from 0 to 4, right? So u equals x squared plus 1. So 0 squared plus 1 is 1. And u would be 4 squared, 16 plus 1. So from 1 to 17 is our integral now. This was over here, it was still 0 to 4. So I need to evaluate this at 17 and at 1. Now those are not any pretty numbers, so we're just going to put it 1/2 the natural log of u. 17, let's go ahead and substitute that. Minus 1/2 the natural log of 1. And I didn't even need the absolute value in there, right?
Suppose we now change u back to the x. X squared constant.
You're right. Thank you, I missed that step too. Common mistake. Don't evaluate it for that, right? So we have to go back and change it. So what was u? X squared plus 1. Actually, let me just leave it right there. And then put it in right there. Well, that's still.
Put it back in, then you shouldn't change.
No, I should. If it was back as x being integrated, I would change it back to x's. But it's u's are 1s and 17, so leave it as it is like that.
So you don't change.
No, because I've changed what
Because you're in terms
u.
of u.
I'm in terms of u right now.
don't change your A and B, then you won't have.
Yes, if you don't change your A and B, then the final step is to change it back into x's because you're integrating in terms of x. Because if, let's just say we did natural log of u, but evaluated as 1/2, evaluated the old x values. The x values were from 0 to 2, 4, huh? Yeah, 4. But now I have to change this. This is x. I need to change that to 1/2 natural log of u was the x squared plus 1. Evaluated at 4 and 0. So you're still going to get the same answer. 17 minus 1/2 natural log of 1. So in the definite integrals, you have two options. You can work with changing your x's, your limits of integrations to the u's, and evaluate that in terms of always u's. Or keep your limits of integrations in terms of x's, and then when you get to the end, getting your antiderivative, in terms of u, it needs to go back in terms of x's. One last one. Let's call it the day. Very similar to what we just did. We did the indefinite integral of sine cubed, I think it was. Or cosine cubed, yeah, something like that. But very similar. So I'm going to let u equal sine x, right? Derivative sine, cosine. So du is cosine x dx. Oh, we have that. This is the easy one. So there's u. So this is integral from 0 to pi over 2. So we're going to think about that before. U to the 4th times du, right? So I need to check these limits of integration. These were for x's, right? So is u a pi over 2 now? This needs to be, if x is pi over 2, what's the sign of pi over 2? Pi over 2, right there, or unit circle, 1, right? So that's 1, so that goes up to 1. What's the sign of 0? 0. So we're integrating with terms with respect to u from 0 to 1 of u to the 4th du. This gives us, if I would have left this, remember, just like the last problem, right? I can go ahead and do the antiderivative, but then I have to go back and replace u with what it was. U was sine x, and then I can integrate with the upper limit sine of pi over 2 or whatever. Right? That derivative with pi over 2, antiderivative with pi over 2. But this one is now u to the 5th over 5. Evaluate it from 1 and 0. And that evaluates nicely, really easily. You don't have to do any trig, right? So that's just 1/5 minus 0 is 1/5. So those limits of integration, if you're gonna change them, that's fine. Let's work with them all the way through the end. If you don't change them, you have to make the substitution at the end. Let's just put that in there for your notes just to show that. If I didn't change these, I would still have this being u to the 5th over 5, right? Evaluated at pi over 2 and at 0, but substitute or back substitute u to be equal to what we said sine of x. And now you can put in there sine of pi over 2 all to the 5th over 5. Sine of pi over 2 is 1. I put sine of 0 all to the 5th over 5. Sine of 0 is 0. It's still 1/5. So you got a couple options. And again, with these, they're definite integrals. Put them in a calculator if you need to see the actual value that comes out, right?
Right.
The values that are going to come out are going to be numbers. Definite integrals are areas under the curve, area, right? So you're not going to get expressions as far as function sine x, cosine x as an answer for a definite integral. An indefinite integral, yes, you will, right? Because you're getting a new function out that represents the area. All right. Question.